Hopefully you're all doing well. Oh, again, I need my OneNote. All right, so let's talk a little bit more about some embedded systems, and what I'm going to do today is I'm going to finish out this chapter, and it's actually not going to take that long, and then talk a little bit about some modifications that I want to make to the schedule. I think you guys will like the modifications, so I don't think it's going to be an issue, one way or the other. All right, so let's jump into this. First, take a drink of water from my really big water glass, right? That's just in case I get super thirsty, right? You never know. Okay, so I'm looking at embedded systems. We looked at embedded systems last time, and we looked at some of the different circuitry things, and then we also looked at the Geschke-Kohn y-axis, logics, the y, sorry, not y-axis, y chart. So that three-part chart that kind of shows or talks about the three different important things in an embedded system, and then there's these concentric circles, and each one then is another level of abstraction as it goes out. Okay, so but what I want to do today is talk a little bit about the software, and I don't want to dig into it too much. I think instead what I'm going to, we'll have an assignment that'll address some of this, but that's a different story. I'll talk about that in a bit. All right, so I just want to talk about embedded systems software. So the difference here is that on a regular general purpose computer, we're going to install an operating system, right? It's going to boot it up and be able to control kind of everything. The problem with that is it doesn't always know what's going on. In fact, it doesn't know how much RAM you have. The operating system can't know how much RAM you have. It can't know all the different components. In an embedded system, some of those things can be dictated. How much RAM has to be here? How much cache has to be here? Or even sometimes the chip is sold with the operating system together, and so then it knows exactly what's inside of that chip, and the chip itself might be even a little bit bigger and have some other features on it, like some RAM, like some input places. And a perfect example of this is a Raspberry Pi. Now, Raspberry Pi is really fairly old right now when it comes to computer stuff, but anything that you could make with a Raspberry Pi is absolutely an embedded system. Okay, so let's kind of go through this a little bit. Okay, and I'm just going to talk about some of the things that somebody who's writing this software needs to think about. Okay. All right, so let me get this. So, embedded systems. Embedded systems. So, I'm going to put this usually. We talked about this a little bit maybe before. Time constrained. So time constrained means that the amount of time that something takes is vitally important. If the embedded system is a pacemaker, right? It's very important that that it works exactly at the speed with which you're asking it to. Maybe less so for your coffee maker, but I mean, if you want a perfect cup of coffee, you got to have it exactly the right amount of time. That's probably not as important, though. Not even close. So, but a lot of embedded systems are time constrained. The timing matters. How fast they go matters. Not all of them, but usually. So because of this, they rarely use virtual memory. And if we remember, what's virtual memory? Well, virtual memory is when I make use of storage, hard drive, solid state drive, a flash drive, something that I write a USB flash drive. Any of those things could be used as virtual memory. But we rarely do that here. And the reason is that if we remember about virtual memory it can be quite slow or at least unpredictable. And that's the biggest problem, is the unpredictability. Because it's so slow to access it, then it needs to be, because we have time-constrained operations, we can't use it, because if we're going to get something to happen and we want to have a consistent timing for it, we don't want to potentially have it take an extra 2 seconds. A perfect example for this would be an embedded system in, say, a factory assembly line. Not necessarily assembly line, but where the factory is kind of doing all of the steps themselves. And I'm sure all of you have seen videos of different processes. As one of them might be the sharpening of a pencil, or even the putting on the eraser of a regular number 2 pencil. That it's important that it puts that on there in the proper time, right? Because it needs to be exact. Because if the pencil's not there when it tries to put the pencil on there, there's a problem. When it tries to put the eraser on and there's no pencil there to put it into, that's a problem. So it also needs to be very precise in lots of other ways. Anyways, that's the reason why we don't use virtual memory, is because sometimes it can take an extra second or 2. But for a normal computer, right, if you click somewhere and it takes a second before it will be annoying, but it's not vital to the process itself. All right, so one of the other things is memory constraints. So memory constraints would be the limits of your memory. So your memory limits. That's another way to think of that. Memory limits are known a priori. I need to redo that because I want to make sure I spell it right, because it's probably a new word for some of you. A-P-R-I-O-R-I. A priori. That's a Latin word. It means, I think it's a Latin word, I don't know. Anyways, it means ahead of time. So if we have certain memory limitations, we usually know them before we start, because embedded systems are sold as systems. A PC is sold, generally speaking, as parts, and then somebody puts it together. And the person who created the operating system doesn't know what all those parts are. And in an embedded system, all of the parts are known, at least all of the central parts. You might have some peripheries that you don't know. In fact, that's actually pretty normal. But you don't necessarily know. You do know, in this case, right? You would know how much RAM you have, how much cache you have, what kind of RAM, what kind of cache. All of those things can be known a priori for embedded systems. Very important. Memory leaks. So if you have a regular, so what a memory leak is when things get allocated in memory, when whatever gets allocated into memory, into our cache or into our RAM, then we save those spaces. We reserve that space for it, and we don't let something new come into those spaces. A memory leak is when we forget to. Let me back up a second. Okay, you guys are used to Python, mostly. Okay, so there's something that goes along in Python. It's called a garbage collector. So when you're done using a variable, right, you created this variable, you called it I, you put some numbers in it, you did some stuff with it, but at some point you no longer need that. So what will happen is the garbage collector recognizes this. It says, oh, don't need this variable anymore. I'm going to go and throw it away. And so throw it away is the wrong word for it. It deallocates the memory. Not super important that we understand how that works, but we do need to know and understand is that in Python there's a garbage collector, or there's a process that goes along looking for variables that you no longer need in your code. And when you don't need them anymore, it gets rid of that value in the memory. So it doesn't keep track of it anymore. In an embedded system, because memory is more precious, and because garbage collector, this is the bigger problem, isn't so much that memory is precious, but that the garbage collector going around doing its thing, it might do it at a time that's inconvenient for our time constraint. Right? If we absolutely need this thing to get done right now, no matter what, if the garbage collector fires up at that point, it might delay us by a fraction of a second, or it depends on the system. It might take a little extra time. Now, as a human, when we're using a regular computer, it's not that much of an issue. Because, well, first up, there's a couple things, right? Normally, our personal computers are going to be faster, right? They're going to run at a higher clock speed, because the embedded systems are usually older technology. And so the garbage collector is not useful to use. And so we have to use languages that don't do that, like C. C does not have a garbage collector. It doesn't need one. Is that right? Does C have a garbage collector? C might have a garbage collector. Now that I think about it, it does. But we can actually modify C, because in C we can deallocate memory. That's actually a possibility to do that. So you can do that manually. So in an embedded system, you're not going to have you don't want to use anything that uses a garbage collector. What you're going to do is you're going to deallocate the memory yourself, so that you can control when it happens. And the deallocation itself doesn't take time, but the garbage collection does, figuring out when something needs to be deallocated. And so the garbage collector doesn't exist, generally speaking, in an embedded system. All right, but this is what the problem is. A memory leak is when When memory gets allocated to be used, and then the system somehow forgets to clean it up, to deallocate it, so it stays allocated, which means it can't be used by anyone else. This is really important. So we've got a memory address, and we're going to say, no, you can't use this. And I know that kind of flies in the face with some of the stuff we did not that long ago, actually, with some of the caching and things, right? When we're talking about bringing in from memory into cache, that kind of thing. And so I know in some ways it flies in the face of that. But this is indeed what happens. We can actually lock things in and say, you're not allowed to write over this. You can't get rid of it. You can't get rid of it. You could change it, but you can't get rid of it. Okay, so memory leaks are very dangerous. So memory leaks are very harmful. I'm going to use harmful. And I ran across the statement. Oh, no, okay. All right, so those are just some things we have to think about when we're doing this. So how are... Well, I guess we've already been talking about embedded systems. This is things that make it different, right? I was going to put how are they different, but that's already what we were talking about. How are they different? Okay. Another thing, so a normal operating system doesn't want its processes to have direct access to the hardware. So you have to go through some kind of a driver or some kind of a some kind of a little piece of program, like a micro program, in order to use a mouse, right? There's something in your computer that piece of software is what's controlling the house. That's why we call it a driver. And so what we want to do is when you want to interact with that mouse or have the mouse interact with you, what you need to do is you interact with the driver as the program. Now, in an embedded system, we actually pull that away. And the reason for that is simplicity, but also when the mouse, so if we're working on a process that's time critical, it's important to get done properly, and the user clicks the mouse inadvertently, just as an example, it wouldn't necessarily be a mouse, it could be something else, but something happens. We don't want the control to pass over to handling that event, handling that thing that event that happened. We don't want to pass control over to that. We want to continue on what we're doing. Now, we can handle that in other ways, but one of the other things we can do is we can actually give our processes direct control of the hardware. Because the system is much smaller, it's less complicated, and so it does that. So this is direct. The other thing is we always know what it is. Like, now for my laptop, I knew what kind of what kind of keyboard is attached to the laptop. But for my desktop, my operating system, does it know what kind of a keyboard I'm going to get? Does it care? No, it doesn't really care. As long as there's that piece of software in there to make that transition, it doesn't make a difference. It has direct access to hardware. Also, clearly defined events and their responses. So we're going to put right in the operating system, we're going to put in the things that we know that they're going to be events, right? A thermostat goes over a temperature of 150, right? That might be an event, and that we clearly know that that's going to be an event, or at least a possibility of an event. Sometimes it's more abstract than that, but that's not a huge difference. Okay. Oh. Okay. If an embedded system solely relies on human interaction for any of it, for whatever it does. So I'm trying to think of an example of this. Okay, maybe it's a silly little, but you get those little handheld games, right? And you push this button or that button. You know, it's not going to do anything unless the human interacts with it first. And you can't even put it into a mode. Usually, you can't put it into a mode where it just automatically does stuff. It's doing things based on you pressing keys. Well, actually, a calculator. That's a better example. Calculator. It doesn't sit there running off its bells and whistles unless you are pushing keys. So, if that happens, it's not as important to get things. It's not as important. Timing is less important. Okay, so if it relies on human interaction, like a calculator, timing isn't as important. Now, I know when you push in what's 6 times 7, you want to know right now, right, that the answer is 42, so that you can, answer that on your exam. That's that's a reference to Hitchhiker's Guide to the Universe, by the way. So, it's not really 42. 6 times 9 is not 42. All right. Yes, unless you're extremely high, writing a radio show. Maybe that seems legitimate then. So, okay. Anyways, yeah, it's not as time sensitive because it's not that big of a deal, right? Because when you press that equal sign, and you have to wait an extra second to get it, it's not that big of a deal to you. It's annoying, but that's it. Okay. So, in a real-time system, so what's a real-time system? That is a good question. Real-time system. Oops. Okay. All right, I just want a definition. Real-time operating system is an operating system or real-time applications that processes data and events that have critical defined time constraints. A real-time operating system is distinct from time-sharing operating systems such as Unix, which generates the sharing, meaning the operating system is capable of monitoring the relevant priority of completed tasks. Switch between tasks based on their priorities, while time-sharing systems switch the task based on clock interrupts. That's actually very good. Okay. A real-time operating system is an operating system in which the time taken to process an input stimulus is less than the time elapsed until the next input stimulus of the same type. Okay. Event-driven. Switches tasks only when an event of higher priority needs servicing. And then there's time sharing, scheduling, algorithm, mutexes. Yeah. Oh, mutexes. That's a great topic. Yeah. Oh, so this is from a different professor. Well, an author. I'm guessing this is a professor, but I could be wrong. Dependent Embedded Systems, spring of 1990. That's a few years ago. Oh, yes, hard versus real. This is actually a good. Oh, this is good. Okay. So hard real time and soft real time. Predictable, degraded, environmental, computer control control of pace is controlled by the real. Oh, very good. Safety, often critical, non-critical. Size. This is good. That's a good little thing there. Oh, here we go. We could get into that stuff if we wanted to, but we don't really want to because we're starting to get really far on the fringes actually of what we're looking at here. Okay, so a real-time system is, well, wait, did I even end up getting a definition? It's an operating system for real-time applications that processes data and events that have critically defined time constraints. Okay. So that means timing matters on these embedded systems in a real-time system. So where timing matters, think about it that way. Where timing matters. This isn't exclusively exactly what a real-time system means, but let's just think about it that way. Responsiveness is vital, which actually kind of makes sense, right? Based on the definition, right? A real-time system means things need to be done in a certain amount of time. It's need to be done fairly quickly. Well, then responsiveness, which is how fast things get done, is important. That makes plenty of sense. So one of the statements I ran across at one point is, if it's late, it's wrong. So that's a way to think about that. All right. All right, so then we also have to okay. We also want to look at the memory. The memory footprint is important. Wow, I'm going the wrong way. The memory footprint is important. So let me explain what memory footprint means here. So what memory footprint means is how much memory a thing takes, a program takes. And in this case, we're talking about the operating system. So the operating system is vitally important that it takes as little memory as possible, because remember, this is a limited resource. So because the memory footprint is a because the memory is a limited resource, especially in embedded systems, it's really important that the operating system not take up that much space. So with that in mind, it means that it's usually modular. So you might think, well, modular home, right? Okay, so that's an example. Well, modular means that we can take and put things in and take them out. So if you buy this operating system / embedded system together, and you're not going to hook up, it has the option for you to hook up a small, memory card or something like that, right? Like a, like a little, not USB. What are they called? It's not the SIM cards. Jeez, I have one at my desk, right here. These little guys. What's this called? I don't even know. SD cards. That's right. That's called an SD card. So, right, has the ability to hook up to a SD card reader or a SD card, right? And so that would allow you to have that more extra memory. But you decide that you don't want to use that. So now, the portion of the operating system that would control that would have direct access to that, it just gets deleted. It doesn't even get installed on the computer. So that's what I mean by modular, right? When you get an operating system, when you get Windows, or when you get the newest Mac operating system, when you get that, you get everything. You can't just say, I don't really want all of the special parts because I want to strip it down. You can't do that. It's not possible. You either get the whole thing or you don't. That's it. In embedded systems, they're usually modular, meaning you get to toggle the switches for the stuff you want and for the stuff you don't want. So you can kind of call it like a la carte. So they try to strike, when they're creating these things, they're trying to strike a balance between offering as many features as you can possibly want, potentially, but also they want to try to be careful and have as small as footprint as possible. So again, that's how they can get around some of that, is by doing the modular, because you say, oh well, we'll do as much as you, we're going to do a lot, but you don't have to take it all. And so we're going to be able to cut some of that back, which then gives you back some of your memory, because it isn't required for the operating system, the embedded system's operating system. All right. I'm going to leave it there. There's actually quite a bit more in the chapter to cover. I don't know it's super vital. So now let me also then talk about chapter 11, which is supposed to be going. Chapter 11 is supposed to go start potentially next week. I previewed chapter 11, and I'm like, none of that stuff is that important, so I'm just going to axe it. And so we're not even going to cover chapter 11. So with that in mind, what I want to do is I need to do. I think I'll have to make a survey for you guys. So on anything that you would like me to go back and recover because you don't think it was covered in enough detail. So that's what I'm going to do is I'm going to make a survey. I can do that in real time just right now. But I want to make that survey so that you guys get a chance to give me feedback. And then we can look that week after Thanksgiving. We've got a week of lectures that week. And so what I'm going to do for the schedule is I'm going to do I'm going to finish up today. We're going to go back and look at some more Maria stuff. And then we're going to do Marie again tomorrow. And then we'll do Marie next Monday. And then we'll be done. Probably be done with Marie, but maybe not. It's up to you guys on how you decide you want to do that. And then the following week, where I had planned to just do chapter 11, then we won't do chapter 11. So I'll do any catch-up stuff that you guys want me to recover and or review type things. And then that's probably all. So we'll see. I mean, I could just keep doing some more live coding. I actually kind of enjoy that. So if you guys want me to do that, please indicate that in the survey. Okay. Also, that week there had been an assignment for there was going to be an assignment for chapters 10 and 11. And that will still be the case, but there won't be anything for 11. And 10 has been very little content. So it will be a different style of assignment. I don't think it'll be too hard for anybody, but I will have a little bit different criteria for it. I have an idea for what I'm going to do, but let me. We've got some time before we deal with that. That's a couple weeks away. All right. So, also, I know you're all waiting with bated breath for exam 2 to be finished. I'm about 2/3 of the way through. I will endeavor to try to get that finished tonight. If I don't get it finished tonight, it will absolutely be finished tomorrow night. And then I will get on to assignment 8. And I also need to go back and do some of the rework too. So I need to get caught up, and maybe over the Thanksgiving break I'll have some time to do that. All right. So close the book. Put this stuff away. Let's just minimize that. Let me get myself a thing here and get Maria open again. All right, so let's upload. Yeah, there our decoder. All right. Now, whoa. This was doing a lot, wasn't it? Oh, yeah, okay. Well, let's see what this does, because I don't remember now. Oh, that's right. It reads in a bunch of... What did we read in? We read in instead of hexadecimal, let's switch it to decimal. Let's go 3. Subtract cent. Wait, what's going on here? So we input, we subtract cent. Where's cent? Cent is here. Cent is 21. That's right. That's right. We were looking at this. So we subtracted cent. And then we look to see help instruction set. When we say 800 there, we look to see if it's positive. So we're hoping for a negative, or we're going to jump to the end. So in this case, we knew that it was a negative, and so that we add cent. We add cent. So we add cent back in, then we subtract our offset, and our offset is the number 0. And then if it's negative again, then we know it wasn't, it was a character if it was negative. So this part here, so we jump to opper. So, oh, that's right. When we get an operator, so this, I'm gonna put a label out front here. Num, caps lock on. So then it does a store I of num a. So there's a number array starting at whatever num a is. Num a is 30. Something didn't work out quite right. Okay, let's go back and assemble. Decimal value 3. Accept. Step. So the accumulator has gone negative to negative 30. Oh, no. Okay, go back to assemble. We want to bring in a Unicode. That's right. That's what we decided. Or I decided. There we go. And it's putting the values in here properly. As long as I don't go over 10, I can continue adding values. So I got a 3, a 4, a 7, a 9, and a 2. All right, so now I'm going to put a subtraction symbol. And it freaked out. No problem. Okay? But see what's sitting here in our accumulator. It didn't freak out, it just halted. What's in the accumulator? So, it got down here, it went back up here to the loop. Okay, let's go back and assemble. Let's try 3. So now it jumps back up to the top. Does the input. I'm going to put, a 5. Step. And then, now I'm going to put the negative symbol. Now, look what went there. 45. Minus, right there, 45. Hey, look at that. We figured it out. Okay. But it's actually 2D, right? Not 30. Okay. Oh, hex 30. So it's 2D. So that's correct. That's what it is. Good. Then we do a step, right? Because we subtracted cent, but it's positive now. So it says if it's negative, skip. Oh, it's still positive. So we're going to add that cent back on again. So we come back to our offset. And then we're going to check to see if it's negative. Oh, we subtract the offset, sorry. The offset was 30, because that represents this. So then it's going to, now we've gone a negative number. So now it's going to jump to upper, and then it just says end. Oh, it says jump to end, which is the next line, and then it loads the open P, and then does an output, and then it halts. Okay. We're gonna have to still have to work with our output and figure out how that's all gonna work. Okay, but here we don't want to jump to the end right away. Let's go ahead and just do this. Tab, tab. Eventually we'll jump to the end, but right now we're not going to do that. What we're going to do is we should now at this point have received, so where did it jump to upper? It jumped to upper from here. So that means we've subtracted our offset. So what we need to do is we need to add our offset back in again. Add offset. Store I. Oops, store I. Now, do I have a place? Yes. Operate. Operate. Then, instead of jumping to the end, I'm going to jump to the loop. I'm going to jump right back up here again and just start on going some more. All right, so let's run this again. 3, 4, 5. We see those going into this op array, or number array, and then I put a negative symbol in there, and then a positive symbol in there, and then a multiplication symbol in there, and then a division symbol in there. Okay. But it didn't advance that. Okay. So we need to deal with that, don't we? Okay. So then let's put in, what did we agree? What was our cent here? Our sentinel. That's right, 21. So 21 is an exclamation point. So when I put in an exclamation point, look at that. It halted immediately, which is good. Okay. In here, in our we can do that first, and then we need to load up A and add 1 to it, and then store up A. All right, let's try this. 3, 4, 5, plus, minus, multiplication, division, exclamation point. So what did we do? So we saved these into these spots here. And we know what they are. This is the plus sign, this is the minus sign, this is the division, this is the multiplication. Oh, but that's not how it works, is it, at all? Right? When we come to an operand, what we need to do, Oh, this is going to get... This becomes tricky as all get out, doesn't it? Yes. Because we have to handle it now. Is this even going to be possible? I'm not sure. Because I need to handle it immediately. Remember? Right? When you're reading along in reverse Polish notation and you come across an operator, you need to pop off the last two numbers or operands, and then you stick it in the middle of them, and then you push it back onto the pile. Okay. Let's try this. Here, instead of storing these into an op-A, let's get rid of that op-A stuff. All right, so we're going to get rid of this op-A stuff. We're not going to store that like that. All right, so we're going to re-add the offset. So let's take the top two things from the code and let's load them in. So first off, we have to determine which step we're doing. Okay, so, yep, okay. So let's add some new things in here. I'm going to call it the addition. Get hex 002B, the subtraction symbol, that's hex 002D, the multiplication symbol, and that's hex 002A, and the division symbol, that's hex 002F. And I got those right from here. Boom, 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 boom. Okay. I could go and look at my ASCII table, and it would say there's multiplication at 2A, plus at 2B, comma is 2C, well, we don't care about the comma, 2D is the minus sign, and the division sign is 2F. Okay, good. Now, what we need to do in this one, oops, is when we get to this, what Opera is going to do is it's going to decide which step or which thing we're going to do. So are we going to do addition, division, multiplication, or division? So let's do a subtract. Come on, get over here. So we added back in the offset because we have to do that, so we can actually get back to what we were originally. And then then we're going to do a subtract, and we're going to subtract the addition. Okay. And then skip condition. Which skip condition do we want? We want it to only skip if it's 0. If it's 0, we want it to skip. Yep, that's exactly what we want to do. So 400. So then I will add. Oh, and then the thing I want to skip is a jump to add add function. So then I'm going to add that add back in again and then do the jump loop. Okay. So add func. And so this, right now I'm just going to do a jump to the loop. Or no, actually, I'm not even going to do that. Yeah, so each one of these will just end in a jump to the loop. So let's go ahead and assemble this and do a run. And go 3, or 2, that's fine, 3. Now let's add in the plus symbol. And what I want to do is I want to see what it does. Ooh, okay. I need to probably be stepping. Okay, let's do a step. 3, step, 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 step. 5. Okay, now I put the plus symbol in here, and I'm going to be curious on how this works. Okay, so 2B went in there like I expect it to. Way to make this bigger. Change it. No, not really, is there? Okay. All right, so now we're going to do a step. Here, it's still positive, isn't it? So that's not going to skip that. And so then we bring back our cent, and then we're going to subtract the offset, and we get a negative number, which means don't skip. So now we jump down to Opper. We add back our offset, so we get our 2B again. Now we're going to add, we're going to subtract our add, which gets us to 0, because our add was 2B, addition symbol. So now it says skip if it's 0. Oh, okay. Oh, yeah, this is not good. That's not what we wanted to do. That's why it wasn't working. Okay. We don't want to skip if it's 0. Oh boy, okay. Continue after the add. Okay, now I put in the plus sign. Okay, so this is what I was hoping to get to the whole time. So the plus sign goes in, and so then we step, and we're seeing that it, right, it's still positive. So we're going to add the cent back on. So now we subtract the offset. We get a negative number. That means we're going to not going to skip, so we're going to jump to the Opper. Okay, so then we add the offset back on again. We subtract our add. We got 0, so we want to skip our Okay, this is where it gets kind of funny. This is a little strange. Maybe it's the first time we've seen this. So I have a condition in there. If I don't skip this, if I don't skip the next one, I'm going to jump down to my conditional add. I continue after the add. Okay? If it is 0, I'm going to skip, and so then it'll jump past this one, and that won't work. This one won't happen either. So then, but if it does happen, okay, wait. If this is true, it will skip the one that'll bring down to our continue add, and it'll then the next thing. This is what's going to happen. It'll get down to our jump add function. So it jumps to the add function. If this is false, then we won't jump the next thing, and we won't skip the next thing, sorry. Then we'll go down to the jump continue after the add, so then it comes down to continue after the add. Basically jumping this. So it's picking one or the other to jump. In this case, it jumped the continue, so it's going to jump down to the add func, and then it goes up to our loop again, and we can add another value. Or open and close parentheses. Our sentinel it was 21. What is 21? Oh yeah, that's right, the exclamation mark. We could have made it a 20, I guess. Although I'm not sure that will work. Assemble, run. Can I just put a space there? No, okay, it doesn't let me. So I have to put some kind of I could put this there. That won't stop it, though. That's okay. Yeah, for now, I think we're good there. All right. So let's go down and work on our add function now. That's the only thing that we're going to try to get to work. Okay. We're eventually going to get a jump loop here, but we don't want one just yet. Okay. So the first thing we're going to do is, remember, we've got a 0 sitting in there, but we don't really care anymore, because what we want to do is we want to pop off the most recent 2 things off of our stack, and we're going to add them together, and we're going to push it back on. So we're not actually going to be able to print out the whole statement, do the conversion here to print it out. That would require more sophisticated. We could do it. It requires a lot deeper thought and actually probably recursion, and I don't really want to deal with that. Not really. So let's instead here, what we're going to do is we're going to pop off the last 2. We're going to actually do the addition, then we're going to push it back on again. So what this will do is it'll actually give us an answer. It'll give us a result. Okay. So now I know it's addition. I'm in the add func, so I know it's addition. So what I need to do is I need to load I. So I'm going to load the thing from the num A. Oh, actually, not num A. From num A, is that right? Num A represents the next open spot. So what I'm going to do is I'm going to load num A, subtract 1, load. Oh, and then I need to store num A, and then load I, because I'm using num A for both of them, right? I can't do another decrementing of num A while still saving this value. So I need to create another variable. Subtract 1 and then store in num B. Num B, comma, x 0, 0, 3, 0, although it's not going to matter. All right, so store that in num B. All right, so then do a load I num A, and then add I num B, and then store I num B. We're going to store it back in num B, and then, well, let's just see if that works first. Unit assembly. All right, so let's do the steps, because I want to step through this. Okay, put the 3 in the correct spot. Goes back to the top. I'll put the 5 there. Back to the top. Okay, now accept this. Scroll up. Step. Okay, got into our here, and so we're going to add that back in so we get this 2b, and then we subtract the 2b. We checked our condition, so we're going to see if we get to our add func. We did. Okay, perfect. All right, so it's going to load num A and subtract 1 from it, and then store it. And then store it back into num B. We stored it in num A, and now I need to store it in num B. Now this one is num B here, so it's going to put a 30. I subtracted another one, so it's going to put 30 in there, which is what I actually want. Okay, so now it's going to do a load of num I. Which brought in that 5, and that's going to add the value here at num B, and then it stored it back right there. Then it goes back up to our loop. Now, num A is pointing at the wrong place. So before we jump, let's load num B and then store num A. Okay, let's just try running this. 3, 5, plus. 8 is stored here. Now, there's a 5 in that next spot, though. Okay. Oh, I didn't need to do that. Okay, I'll show you why here. So let's put in the number 7. See what happened? It got stored here. It overwrote something. I didn't want that. Okay, so let's do the exclamation point and get out of here. Okay. Nope. Sorry. Restart. Doesn't matter. Okay, so I don't need to do this. Num A is already pointing at the next open spot. I had it correct. Okay. All right, let's try this. 3, 5, plus. Let's try this. Yeah, plus. Okay, we got our 8 there. Now let's do a 2 and a plus. See what happened? It put the 2 here, it covered up the 5 that was there, and then it put this in hexadecimal A. Good. That's A is 10. All right. So now let's do 5, 5, 5, plus. See, it did the 5 plus 5 is A, and then plus again. So it'll be a 15, which is F, and then A plus F is 19. Or 25, as it were. And that's doing that right down here. So it looks like we're super close to being done. Because right now, right, I put in 3 5s in a row. And then I started giving it its operators. So it's working perfectly for addition. Okay. We only have a few more minutes left. So I think what I'm going to do is I'm going to end it today. And tomorrow I'll pick this up and we're going to finish it. Not only are we going to finish it, but then we'll also be able to kind of maybe do some things with the output. And then maybe go in and do some things like changing, like this open parenthesis and close parentheses. I think we can probably take those out. They're not really doing anything for us. They were there. So actually, I can make that fix right now. And then I can get rid of these 2 values, thus shrinking our program a little bit. But we see here our actual work runs all the way onto this line here. And it's going to keep going, and so we're going to have to push down our num array. But that's fine too, eventually. All right. So let's go ahead and save this. I'm going to download this. I'm going to call it, make sure I do this. And what was it called when I brought it in? I have to look at my desktop. Reverse Polish notation. Decoder. I'm probably going to end up changing that. That's okay. Take that, drop in here, place the file. Then look at that. All right, so I'm going to save. This is already saved, so I'm gonna replace the file that's up there right now with this one. Actually, I'm not going to do that. What I'm going to do is I'm going to add this one to it so that people get the transition ones are there. All right, so I'll put this up, and I'm going to save. There's not much there, but there's a little bit there, I guess. Very good. And I don't know. I have to look in there to see. That's okay. All right. I think I can say goodbye to the op. the OneNote. Maybe not. We'll see. All right, that's all I've got. We will talk to you guys in actually less than 24 hours, at least of my time. In your time, it might be just in an instant if you're going to watch these, you're going to binge watch these over the weekend. All right, talk to you guys later. Bye-bye. An instant if you're going to watch these.